Alright, after many lessons of buildup, we finally come to what I would call the first real instance of true static equilibrium in this course. When I say true static equilibrium, what I'm really referring to is that we're now going to include the whole suite of our two-dimensional models for equilibrium. Now, before we can charge off into that area, we have to be able to understand that what we're really doing is creating models of forces, we're creating models of structures, and this new piece is models of the foundation. Up until now, we were really just dealing with force components, the idea of moments, and then concurrent force systems. We didn't really talk about what was going on with the foundations or the supports along the way. So let's take a look at some pictures of some real supports. Bridges are a really great place to see these kinds of things because the way that we schematically represent them look an awful lot like the real system. So for instance, here we have what's called a roller support, and it really does look like this big steel roller that is there, right? And in the slightly darker one, you get to see there's this little triangle. This is hard to see, I know. You might look up in Google or whatever your favorite search engine is for bridge supports or a roller support, and you'll see something like this. There's three little roller bearings here so that the bridge can slide back and forth on roughly a horizontal plane. Now this one that you see down here called a pin support is really associated with a little strut in a, you can see these are window units. So this is a building application. On a larger scale, you would see it also in the bridge, but instead of having those three rollers or rockers, you would instead see that fixed firmly to the foundation, and the pin would be up in here. You can sometimes barely see that. Right? And here it's very clearly it's a single bolt. Now in buildings, as in the structural columns, instead of a little strut associated with a window, what you'll see at the base of a column is this little wide flange shape. Here's the wide flange here, there's a flange here, this is the web. In cross section it looks like an I or an H depending on how you turn it. And we have a bolt here that anchors into the foundation, and one on the other side of the web, just two of them. Right? And that would also be a pragmatic example of a pin support. To understand why it acts as a pin support and not this fixed support down below requires the next course in structural mechanics. A little bit of a hint towards it, though, would be when you see this fixed support, then you oftentimes, not always, will see these little stiffeners around the edges of either this tube or this pipe column that you see here. This much thicker base plate and these oftentimes little pieces here that are stiffeners, and that these anchor bolts are many and they're all around the edges rather than inset, is a direct indicator that these are fixed supports. So let's get into a little bit more about just why they're called roller pin supports and fixed supports. Those are the three basic ones. There are a lot more of them out there, but it's all in the end going to be associated with what displacements are constrained. That is the absolute final key. And you won't hear a lot of people talk about that. They'll say reactions are the forces necessary for equilibrium. That's true. However, a more general statement is that they're the force necessary at that specific point in the structure so that a specific displacement is zero. So, for instance, when you see a cable here, and we draw the free body diagram of this part cutting the cable, you'll see one and only one force, and it's saying that there's something constrained about the displacement along that line of action. Doesn't, in a cable case, especially if we include the flexibility of the cable, well, then that might stretch a little bit, but the key is going to be you don't have unrestrained displacement along that line of action. So you have one and only one unknown here that goes along with a zero displacement along the line of action of that one unknown force or reaction component. Right? Now on this one we have a smooth surface. That means no friction, and so all we have is a normal force there, so there's no displacement in the normal direction, and that means we have to have a force in that direction to prevent that. Right, so again, one unknown force component. Here we have a rough surface, so we pick up a frictional component as well as a normal. If we're at impending slip, well, then we know what the relationship is between the friction force and the normal force, but otherwise we don't. There are actually two independent forces there. It all depends on the conditions of the analysis. But for sure there's going to be no unrestrained displacement in the normal direction, and there's a little bit of restraint depending if there's slipping or what's going on in the parallel condition or tangential condition. Right? The roller support then is a more general kind of situation where we have this one unknown force component that is perpendicular to the surface, which is allowed to displace. Such as what you see here. A lot of times they're on horizontal surfaces. People think, oh, it's a roller support. These are the four common different symbols, and they think that means all roller supports then would have a normal force that's vertical. No, not necessarily. It could be inclined. Now, sometimes people get confused. They take these little diagrams a little bit too literally. In each and every case, depending on the author, but in most authors' textbooks, they are indicating here just a simple symbolic representation. There is no displacement up or down on this thing. So if this thing tries to lift off, there's a hold down force as well, even though you might not initially think about it because you think you see a wheel and gee, I can lift the wheel off of that like a shopping cart. And if you literally do mean that, well, then it does mean you only have a compressive force between those two parts. But generally speaking, we don't mean that. We mean that there's a hold down potential as well. Might depend just a little bit on the problem statement and that particular author and the graphic artist. Right? This freely sliding guide is the same thing as a roller. It acts in the same way. You can incline these. You see these in window units an awful lot. Same kind of situation, but one and only one unknown in those. You come to the pin support, and now we have two displacements that are going to be equal to 0. Now we typically are going to represent that as x and y components are 0. Right? That would be the common way to do it. So we'll need two forces to do that. Now, once you calculate what those magnitudes are, you could resolve those into a single force at a direction. Now, if that pin is not free to turn, we pick up another unknown. So that would mean there's friction in there. We usually are saying that this is a friction-free pin, so two and only two reaction components. They're independent of each other, and they are holding those displacements to be 0. Now, the built-in or fixed support occurs in a lot more ways than what you see here. And I'd argue that you don't usually see the symbols like this at all. Instead, you see these little hashing, and then you see the structural members sticking out. That's, I think, a little bit more common as a schematic representation. There, we're now going to have all three displacements are going to be 0. That's going to be translation. So delta x equals 0, delta y equals 0, and a rotation will be held to 0. That means we have to have three forces in order to do that. Now, the reason why you see the symbols F, V, and M, F is usually meant to be the axial force, right? V would be what we call a shear force. It's always parallel to a plane. And then we get this M standing for bending moment for the beam, but moment from a global kind of perspective of the structure. Again, these three are necessary so that you have three displacements that are equal to 0. Now, special situations here on forces and modeling. A body force is the gravitational force. We'll usually lump that all at the center of mass, W equal mg. If you have a flexible support that you're trying to model, well, then you'd use the F equals kx model. For the linear model, it gets much harder if you have a nonlinear relationship going on there. So because of that, we oftentimes will do an approximate linear model when we have something that is nonlinear. Certain soil conditions might be like that. Certain elastic polymer elastomeric bearings can be like the nonlinear kind of system. And this adds some complexity to the system depending if we're statically determinate or indeterminate. And whatever we have for linear action, we also have for rotational kinds of action. Right? And the spring properties are things that you learn about in the mechanics of materials course. Right? So that's the modeling of how we do things. We're going to start applying these models in the next series of examples, and we'll do that in the next video. Hey, stop the video.